بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله. أنا غفران القضاء وحابة أحكي اليوم عن Dynamic Light Scattering. Over the years, the scientific importance of nanoparticles for biomedical application has increased. طبعا زيادة استخدامهم in biomedical application due to different reasons. أول إشي very high stability and biocompatibility. بالإضافة للlow toxicity، هذا خلى النانو بارتيكلز تكون as a target drug delivery system. وبالإضافة لموضوع كثير مهم بالنسبة للنانو بارتيكل size. A range of nano particle size from 10 nanometer to 1 micrometer, as well their optical properties allow them to be studied using microscopy and spectroscopy techniques. We can evaluate the nanoparticles characteristic evaluated by two methods: dynamic light scattering and zeta potential. بالنسبة للدايناميك لايت سكاترينج كتير مهم نعرف ليش يستعمل. مبدئيا هو يستعمل to measure nanoparticle size and evaluate stability over time in suspension at different pH and temperature condition. والطريقة الثانية اللي هي احنا بنعمل evaluation للنانوبارتيكل عن طريق الزيتا بوتنشال، اللي هو بيستعمل to characterize the nanoparticle surface charge and obtaining information about their stability and surface interaction with other molecules. Nanoparticles composition. Nanoparticle composition can be made of different materials, organic or inorganic, such as metal, polymers, carbon nanotubes, and liposomes. The use of nanoparticle-based drug delivery system has increased due to their controlled release reservoir content, leading to a decrease in undesirable side effects. In general, dynamic light scattering بيكون بالطريقة هي اللي هو detection of the light scattered from the interaction of light with a matter gives information related to the physical characteristic of the sample. Typically, in light scattering experiment, the monochromatic beam is directed to the sample, and then detector record the scattered light at a certain angle. Dynamic light scattering measure the intensity of the light scattered over time, when the intensity is correlated at several time points. يعني بكل مرحلة بكل وقت معين بيكون intensity مختلفة عن المرحلة اللي بعديها. بالبداية بتكون الintensity similar، بعد بشوي بيصير losing less due to particles movement. بصير تتحرك البارتيكلز فالintensity بتخف كتير. Then for small particles, the diffusion is much faster. Photon correlation is lost faster, and the correlation decays at early time points as the measurement. However, طبعا بالعكس تماما, large particles diffuse more slowly. The similarity of the intensity over time persists for longer periods, leading to a longer time for the photon correlation to decay. Dynamic light scattering intensity مثل ما احنا شايفين بالفيجر اللي قبالنا، A و B بيمثلوا small particles و C و D بيمثلوا large particles. The correlation function is obtained from the intensity fluctuation in the respective time frames. Small particles A و B diffuse faster with correlation decay at early points. مثل ما احنا شايفين ب B بيكون الديكي أسرع. والlarge particle C و D diffuse more slowly, which implies a longer time for the photon correlation to decay.
Hello, this video will give you an introduction to the dynamic light scattering technique. DLS is an optical technique used for analyzing dynamic properties and size distribution of a broad variety of physical, chemical, and biological materials suspended in a liquid. These can be colloidal particles, bubbles, droplets, or molecules. DLS determines the size of particles in suspension where particles randomly move as a result of Brownian motion. DLS measures the speed of the particle to obtain diffusion coefficient. There is dependence between particle size and particle speed. Small particles diffuse faster, large particles diffuse slower. Instrumental setup is simple. Sample is illuminated by a monochromatic laser beam. Particles scatter the light. The interference of scattered waves generates scattered light intensity signal. Since suspended particles undergo Brownian motion, this motion results in fluctuations of the scattered light intensity. As a result, we obtain plots showing intensity changes with time. We can see rapid fluctuations for smaller particles and slower fluctuations for larger particles. Another important part of the system is correlator. Correlator takes very rapid snapshots of scattering light, nanoseconds and microsecond scale, one after another. Then these changes in light intensity with time allows computing correlation function. Then we analyze this function to get diffusion coefficient of the particles. Then if we know diffusion coefficient, we can calculate hydrodynamic diameter of the particles using Stokes and Stein equation. So hydrodynamic diameter is a hard sphere that diffuses at the same speed as the particle being measured. So regardless of the particle type or shape, whether it is a core shell particle aggregate of several smaller particles or particle with irregular shape, we still use a sphere to model particle diffusion. Hydrodynamic diameter depends on ionic strength, surface structure, and shape, particle shape. DLS analysis gives information about average particle size and also provides size distributions. These size distributions can be weighted by intensity, volume, or number. In number distribution, every particle has equal weighting. For example, the 5 nanometer particles is equivalent to the 50 nanometer particles for number distribution. However, if you look at the volume distribution, the 50 nanometer particle has 1,000 times as much volume as the 5 nanometer particles. For DLS, we normally report size distribution by intensity. Note that intensity is proportional to the radius of the particles in the power of 6. So this technique is very sensitive to the presence of larger particles or aggregates. This slide shows one of the DLS applications. The study was focused on how storage conditions affect particle size. Samples were stored at 3 different temperature regimes and then measured by DLS, which provided size distribution, which is percent intensity on y-axis and particle diameter in nanometers on x-axis, then average diameter and polydispersity index. Polydispersity index estimates the width of distribution. You can see that samples that underwent 5 freeze-thaw cycles, green line on the plot, shows larger average diameter and higher PDI value, wider size distribution compared to other samples. The second peak at about 700 nanometers suggests particle aggregation at these storage conditions. In summary, DLS has the following advantages. It's non-destructive technique and sample can be recovered. The measurements are fast, few minutes. Small sample amount needed, less than 1 milliliter, and we can measure very small particles. However, the disadvantages of this technique, it has very low peak resolution, it emphasizes large particles and smaller particles can be hidden, and proper dispersion can be challenging for some particles. Typical applications include the following materials: protein, biological cells, polymers, micelles, vesicles, carbohydrate, nanoparticles, gels. Finally, these are technical specifications for our DLS system, Malvern Zetasizer. We have at MCL, and you can read more in details on our website. Please contact me if you have any questions. Visit our website if you want to submit training or analysis requests, and I hope to work with you in the future.
Zeta potential. Zeta potential is the potential measured at the slipping plane of the particle under an electrical field. It reflects the potential differences between the electrical double layer of the electrophotic mobile particles and the layer dispersant around them, aqueous or organic environment at the slipping plane. The electrical double layer surface of particle in solution developed instantly and is formed of two layers. The inner layer is so-called stern layer, is composed of opposite charged particles tightly coupled to the core of the central particles, and the second layer أو بنحكي عنه outermost layer is diffused layer consisting of both opposite and same charge ion molecules. When an electrical field is applied to the sample, the particles move to the opposite electrode within the diffused layer. There is a hypothetical plane that acts as an interface between the moving particles and the layer of the surrounding dispersant while the electrical field. As we said before, for the nanoparticles and the zeta potential, this is schematic. Represent the double layer that surround the nanoparticles in aqueous medium. Considering that it has negative charge, the nanoparticle represent as an example is composed by negatively charged phospholipids, implying a first layer stern potential mainly composed by positively charged counterion. After application of an electrical field, the second layer, zeta potential, is diffused layer that is consist of both counterions and ions of the same charge of the nanoparticles, which contact the organic or aqueous environment. And بشكل عام مثل ما حكينا من قبل إنه nanoparticles إلها uses كتير كبيرة as a therapeutics due to very high chemical stability and very high biocompatibility and low toxicity and directly activity or by encapsulating poorly soluble drugs surface composition. كمان وجدوا إنه بعض النانوبارتيكلز لهم very high antimicrobial activity مثل الزنك والنيكل والكوبر and were considered perfect candidates for magnetic resonance imaging techniques presenting a dual activity, therapeutic and diagnostic. Their use in bandages, implants, prostheses is already becoming common, but overproduction for reactive oxygen species in a long-term usage has raised concern regarding the toxicity of magnetic nanoparticles. كمان هي disadvantages of nanoparticles as we said before. Finally, as a conclusion, in future studies, light scattering should be essential for characterization and development of nanoparticles applied to the therapeutics, which don't invalidate the fact that other techniques should be also used to further confirm the conclusion obtained.